Hello, my name is Cesar. Today I'm gonna talk to you about computer architecture. I'm gonna explain two basic models of computer architecture, and well, those models are the von Neumann model and the Harvard model. But first, let's check what do we need to build a computer. To build a computer, we need basically three things. We need the central processing unit, that is the CPU. We need memory and input and outputs. Input is what the computer reads, for example, from peripherals, and output is something that the computer can store in memory and then show to the user using as well peripherals. So in the central processing unit, the CPU, we have also some smaller components. The ALU, that is the arithmetic logic unit, performs all the computations and calculations such as additions, subtractions, logical operations, bit shifting, etc. We have also the control unit. This part handles all processor control signals. It directs all input and output flow. It fetches code for instructions and controls how data moves around the system. We have the registers, for example, the program counter, the memory data register, and the memory address register. The program counter keeps track of the memory location of the next instructions to be dealt with. The PC then passes this next address to the memory address register. So this counter tells you what instruction comes next, or tells the processing unit what instruction comes next. The memory address register stores the memory locations of instructions that need to be fetched from memory or stored into memory. And the memory data register stores instructions fetched from memory or any data that is to be transferred to and stored in memory. An accumulator that stores all the results from the ALU, and buses to connect all systems. So let's check first the von Neumann model. In this model, the main characteristic is that we have just one memory for the instructions and also the data. So everything is stored in a single memory. You can see, for example, there in the diagram that we have a bus for the data and the instructions. We don't have separate buses. It's just one bus to connect the CPU and the memory. What are the problems we did with this structure or this architecture? First, we have the so-called memory address bottlenecks. Since it's just one single memory, everything has to be sequential, and we need to wait for the data to be stored in order to execute the next instruction. So programs and data are stored in a single sequential memory. Also, there is no explicit distinction between data and instructions representations in memory. That means that there's no distinction between data and instructions. This distinction has to be brought about by the CPU during the execution of any program. So that means more computations. We have also a one-dimensional memory requires a linearization of data structures in high-level programming languages. For example, if you use a high-level programming language, and you want to implement complex data structures, these structures have to be linearized by the CPU in order to store them as a linear structure in memory. And last, we have the data representation does not retain any information on the type of data. Sorry. There is nothing to distinguish a set of bits representing floating point data from that representing a string, for example. Such distinction has to be, again, brought about by the program logic. So this is what is called the semantic gap. Not being able to represent dimensional or high-level structures or different type of data at the memory level. What are the advantages? Well, it's a practical structure for digital computers. It's a very basic one, and you can build one very easily. And that semantic gap I was talking about has been solved by several compilers that have developed to eliminate this semantic gap. So they utilize the developments. All the compilers have advanced to solve this issue, this semantic gap. Now, the Harvard architecture is a little bit different. This architecture is called like this. Its name is due to the work on Mark 1 to Mark first to Mark 4 computers at Harvard University. And well, the main quality of this architecture is that we have independent paths for data addresses, data instruction addresses, and instructions. So we have different buses that direct all the information to the memory. In the past, the memory was separated in two different memories. It was two different memories. Nowadays, well, this architecture uses only one memory, and and the bus is just the buses, or the memory is partitioned into different sections. But in the CPU, we have basically the same. We have the program counter, the registers, and the ALU with the accumulator, and of course the input and output unit. The advantages with this structure is that we have separate memories for instruction code and data. This allows data pipelining, so we have fetch for instructions while also performing computations in the ALU. We can read and write data at the same time. That was what I was talking about. You can perform a computation and also read the data and write data into memory. So here we have all the two differences. We have, for example, here the von Neumann bottleneck. Explain here how the instruction and data are in the same memory as a linear structure, and we have two separate memory blocks. The problem, well, with the Harvard architecture is that, well, as the number of buses increases, also does the complexity of the system. So maybe it's a little bit more difficult to create this kind of systems because we have so many buses for data, for instruction, and addresses. Thank you very much. I hope that it was very explanatory.